Oh, the remote control. Remote control, I did not. Спасибо.
So, ladies and gentlemen, let us start our morning session. Series of lectures of interest and
Good morning, colleagues. Let me start my third lecture, and it will be about application of gamma convergence and Günther's derivatives to the problems of thin bodies. Well, thin bodies mean, for example, the natural shells and so on. But of course, in engineering, such shells are not interesting. So, in engineering are interesting shells of construction of thin structures. And a lot of models exist about thin structures, shell models, and we contribute one more model, but we think that it is worth to contribute one new model because engineers apply it quite often, and we hope that our model also will find its application because it's rather simple and natural. Why simple and why natural? I will try to show you during the last two lectures. In this third lecture, I will speak about heat conduction by a thin structure. And in the next last lecture, we'll speak about more complicated problem of shell problem, how to describe the deformation of the thin structure. What is the problem here? When you see the thin structure, what does it mean? That the two dimensions are much larger than the third one. And the attempt to represent the deformations of such body with the help of two-dimensional equations is very important. Imagine if your calculations of such structures in two-dimensional case takes, for example, 10 hours on the computer. In three-dimensional case, it might take many times more. So it is important to have the two-dimensional description of this three-dimensional problem. So after such introduction, let me show you more concrete things. What is this thin structure mathematically? How to pose the problem? We take a mid-surface C, you see it here, mid-surface. Oh, I forget as always to switch. Yes, we take a mid-surface. You see here mid-surface and some layer around it. It's represented here mathematically in the as a direct product of surface with minus epsilon epsilon. We consider equation in this domain and then try to send epsilon to 0 and try to derive the corresponding equation with the help of gamma convergence. Why gamma convergence? I mentioned in my second lecture that gamma convergence is a very natural limit for such problems because it maintains infimum of the problem of the functional, maintains infimum when you go to the limit. And the infimum of the functional, energy functional, in mathematical physics is exactly what the mathematicians and mechanists look there, because this minimum realizes the solution to the corresponding equation if the energy functional is constructed well properly. Okay. What we do now, we consider this representation of the scene structure, and before describing the formation for shells, we describe, as I told you, heat conduction, because heat conduction is represented by one-dimensional equation, Laplace equation, and we also don't consider, although it's not much complicated to consider time dependent, we consider stationary heat conduction when it is independent on time, but with time dependent is also no problem to consider with these tools. But with shells, it's much more complicated because then you deal with 3x3 system of differential equations, and taking limits and calculating limits is much more involved and complicated. We start with a stationary process of heat transfer. Okay, I told you this. Well, stationary heat transfer, yes. Stationary heat transfer process in thin isotropic domain is represented by Laplace equation. So in this thin layer, we have Laplace equation. Delta T is equal to F, where T is the temperature distribution and delta is the Laplacian. Well, Laplacian, of course, standard Laplacian, because we have R3. And, well, the equation has endowed with the boundary conditions. What are the boundary conditions? Boundary conditions that on the lateral surface we have 0. I mean, on the lateral surface of our thin domain, where it's clamped, for example. And in the upper and lower faces, we have this condition that heat flux is given. The normal derivative of the temperature is presented. Normal derivative of temperature, it's heat flux. Okay, consider this problem. Yes, nu is a normal derivative, which in our case coincides with the derivative across the variable which is orthogonal to the mid-surface. But I will speak about this later also. We impose constraints, following constraints on solution. We consider weak solution. I mean, weak in the sense that this solution will look in the Sobolev space. Yes. We look for the solution in the Sobolev space. Here is the, oh, with delay, it runs back. Oh. Sorry. Yes. This is the conditions for this solution, weak solution. For the right-hand side, we're supposed to be in L2, solution in Sobolev space or Bessel potential space H1, and the fluxes are in H half. So traces of H1 on the upper and lower faces. Okay, we need also the so-called Lebesgue point. For the function, Lebesgue point is the following. If such integral, if the integral from the function from t0 minus epsilon to t0 plus epsilon divided by 2 epsilon has limit when epsilon goes to 0, then we say that this point is Lebesgue point for this function. We will need this constraint later for the right-hand side function f. For example, it's very easy, of course, when f is continuous simply, then this limit exists, but it exists also in other cases. Okay, L2, you know, it's square integrable functions. H1 is the functions which are in L2 and together with their derivatives and so on. It's called Sobolev space. And well, you know, but let me give tribute to this very, very famous and very good mathematician, Andrei Lvovich Sobolev, who was first director of Novosibirsk Mathematical Institute when the Novosibirsk University was founded in 50s. And he contributed a lot had many disciples and was a member of the Soviet Academy of Sciences and a famous scientist. Our investigation and our approach is based on the representation of the Laplace operator in the form which I write here down on the last formula. You see it, this formula. What is here? The Laplace operator is represented as Laplace-Beltrami operator, delta S on the mid surface, plus normal derivative. One can say it's normal derivative. And everything is based on this because we sent this thickness. It means this direction where the normal derivative is taken, we send to 0, and we will work with this. And the Laplace-Beltrami operator will remain stable, unchanged. This was the key point here because before the approach was only for the same things was done for plates, and there everything was natural. You have when you have plate, you have the natural coordinates, which are one is orthogonal to others, and here we introduced it with the help of Günther's derivatives. Oh, again, something is wrong here. I think we are. Oh, I am lost where we are. Oh, we went back. Sorry. Yeah. Well, Laplace-Beltrami operator, we have spoken about it. And here is presented how the Laplace-Beltrami operator is defined in classical geometry. You see here, in classical geometry, the form of Laplace-Beltrami operator is quite complicated, one can say, because it's written with the help of the contravariant metric tensor. Contravariant metric tensor. Module of G of this tensor is the determinant, and G upper indices IG is simply the entries of this metric tensor. With the help of such, this represents the Laplace-Beltrami operator in classical geometry. Okay. Our representation is, at least it looks much simpler, yes? It's sum of squares of Günther's derivatives. Okay. Here, small information, sorry, about Laplace. Everybody knows who was Laplace. Marquis, French Marquis, who was very influential mathematician and contributed tremendously in mathematics. And much less was known Beltrami. Eugenio Beltrami, who also contributed much in mathematics. He lived in 19th century as Laplace. Yes, and well, let's continue. Well, in 2004, Dorina Mitria and Marius Mitria, they are Romanian mathematicians, but working in the United States for a long time now. We have proved that the Laplace-Beltrami operator is represented as it is here, but you know this. I have spoken about it the first two lectures also. It's represented as this square, well, sum of square of Günther's derivatives. Okay. And here is how the Günther's derivatives are defined with the help of normal derivative and the normal vector field. Well, Günther's derivatives were introduced, I mentioned it, by Nikolai Maximovich Günther, who lived until 41 in Soviet Union. He is ethnically German, but lived in Soviet Union. But it was rarely applied, only in three-dimensional elasticity. I was speaking about it also. And Günther's derivatives are tangent. Yeah, okay. This, I have also spoken about it. No, it's not listed, not changed. Wait. Oh, but I think it's again wrong. It went back, I think. What is... Yes. Operators in a layer domain. Now we have to rewrite everything in the layer domain to work with it. And what we are, here I remind the equation, Laplace equation in the layer domain, zero condition on the lateral surface, well, on the lateral surface and upper and the lower surfaces we have heat flux, which are known functions. Okay, consider a layer domain. Yes, again, it's a direct product of the mid surface with minus epsilon epsilon. And let's continue. Yes. Now we have to introduce new coordinate system because we have carved domain and we need new coordinate system. Our new vectors of our new coordinate system are projections of the natural basis from Rn. I was speaking about it. DGs, which are projections of EGs, natural basis, are obtained by subtracting the normal projection of these EGs. Okay, and they are, of course, linearly dependent, these DGs. And any function, any vector can be represented with EGs uniquely and with DGs non-uniquely. But if we impose the condition written here in 45 that the last coordinate is defined as the projection, then it becomes unique. And we will keep this always, and we will have representation will be unique also with DGs, if we have some agreement. Yes, and well, we will use this representation in our approach. Yes, and these first n vectors are chosen so that they are orthogonal to the first coordinates are chosen so that they are orthogonal to the normal vector, and then it's unique. Representation is unique, yes. And now we need extended gradient. Gradient, you know, on the surface we have the Günther's derivatives, and with the Günther's derivatives we have Günther's gradient, which is again linearly dependent. What we add here, the normal derivative is n plus first n plus one component. It is orthogonal to others. With this direction is orthogonal to others, everything is okay, but nevertheless, it's linearly dependent, but nevertheless, we need such an extended gradient and extended divergence. And the Laplace-Beltrami operator also we will write as the composition of those extended gradient and the extended. And what is true, because such a representation depends on the coordinate system which you choose. We have chosen coordinate system DG, linearly dependent coordinate system DG, which has n plus one vectors. If you rewrite the Günther's the divergence and Günther's gradient in this new coordinate system, you will get the extended gradient and extended divergence. And here what difference is that the divergence is not just simply adding the component. It also contains now the lower order term, as you see in formula 47. It contains lower order term, which is compiled of one of the multipliers is the mean curvature. Mean curvature, yes. Okay, mean curvature. Next slide. Yes. Lemma, written in full system of vectors. DGs are not linearly dependent, but it is full system. Any vector can be represented with the help of this. I have noted this before. The gradient rewritten coincides with the Günther's gradient rewritten in this system coincides with this extended gradient. Divergence also coincides, and the Laplace-Beltrami operator also is represented. And that's what I was speaking. Laplace operator now is represented as Laplace-Beltrami operator plus the derivative in the normal direction, derivative with dt. Okay, now we have all this representation. Now we can work about reformulation of our problem in terms of functionals, because we can consider gamma convergence only for not the boundary value problems, but only for functionals. That's why we now start the variational reformulation of our problem. Okay, we know about domain, what is omega epsilon. It's a layer domain. And we consider this heat transfer. Here is the boundary value problem. With G, and now we have a bit written a bit general formulation of the boundary value problem, but we will, on the first stage, we will get rid of G. It's always possible to reduce this problem, 49A, B, C, D, to reduce to the problem when G is equal to 0 in the 49B. How we subtract something, and it changes, of course, the right-hand side and changes these fluxes, but well, the problem is reduced normally to the case when we have the lateral surface, we have the zero conditions. Here is a bit more general equation. It is we call it anisotropic Laplace equation. When between divergence and gradient, we have the matrix K, 3x3 matrix, which is positive definite, and that's in formula 50, what we require from K, positive definite. And then the result is that this operator is actually positive definite. This anisotropic, pardon? Oh, slide, sorry. We are not there where I am here. Yes, previous slide. Yes, here is this condition for on the function. This is the condition on this K, and then we have the positive definiteness of the operator. No, it's not written here, but it is as a result. Matrix is positive definite, it becomes the operator for positive definite. And here are the conditions, again repeated, about G and Q plus 1. Weak setting of the problem is weak. Okay, and here is now the functional. Functional is written when G is equal to 0 in this case. It's necessary also to have this, to write this functional that will be equivalent to the boundary value problem. What is the equivalence? If you find the infimum of this functional in 53, functional f, then T, if it is infimum of this functional, it is solution to our boundary value problem. And vice versa. If T is solution of the boundary value problem, it makes this functional infimum. There is a one-to-one correspondence. Okay, and we can work further with this functional and consider, now we want to consider its gamma convergence. We will try to send epsilon to 0 and find the limit of this functional. We will consider a bit more general. It can be done also for nonlinear case. Here is in classical case, this is the bilinear, but one can consider more complicated nonlinear case. So consider such functional, which depends on the gradient of the temperature of T. Okay, and what we need here to impose this quadratic estimate on the function f, on the kernel of the integral of this energy integral, quadratic estimate, which is automatically fulfilled in our case. Well, now when we have this formulation, what is our problem? We send epsilon to 0 and we'll try to find the gamma limit of this integral operator, of this functional. And for this, from the book of braids, we find a lemma which helps us. And these quadratic estimates, they place an essential and central role. Quadratic estimate is very essential. Okay, now we are looking for the minimizer of this energy functional. Okay. Energy functional. We introduced the coordinate system. It was introduced also earlier, but here we repeat it. And well, with these DGs, and we know that under certain conditions, this coordinate system representation is unique. We apply this. It's interesting that the scalar product, we have this x0, y0, they are the coordinates with index g. They are coordinates in this linearly dependent but full system of DGs. But nevertheless, it maintains the scalar product. If you take the scalar product in Rn or take in these coordinates, they coincide. And also the norms coincide. It's written all here. Manipulating with this coordinate system and with these coordinates, it doesn't change essentially the problem. Gamma limit of an energy functional. No, we have this energy functional, but we have to scale it. If we send simply epsilon to 0, does not change anything. I mean, does not divide by epsilon or does not scale it. I mean, the last variable varies between minus epsilon, epsilon. Then we cannot take any limit. We have to fix this variable in minus 1, 1. And send then epsilon to 0. For this, we divide this last, or one can do so, this t, which is between minus epsilon, epsilon, is represented as epsilon tau. And then tau is between minus 1 and 1. That's the first step. Another, the whole, this integral is divided by epsilon. And now we will try to, this means scaling this energy functional. Yes, it's here. Scaling is here. And next step is to continue. And this energy functional has this quadratic estimate, as I told you. Quadratic estimate, which is written here. And also, it is convex. Convex and has quadratic. The first line here shows you that it is convex, and the remainder states that it is It has quadratic estimate. So with these properties, we can continue now our convergence and send epsilon to 0. This result was known only for plates, as I told you. This was the paper in 2002 by Frieseke, James, and Mueller, who have derived the equation for plate, two-dimensional plate, from the equation of three-dimensional thick body, but flat one. And we applied the same approach, but with Günther's derivatives, and obtained our result. Next, we have to perform the scaling of the variable. Yes, I told you. T is equal epsilon tau, and now tau is between -1 and 1. And write everything here, divide by epsilon, and then we send it to 0, epsilon. And, well, here is the division, 1 over epsilon, energy functional, divided by epsilon. And now we can go to the limit. Well, it's not quite easy process. The proof is on several pages. Oh, I think I made a mistake, yes. But the result is that this limit exists. We have proved, together with my colleague Tengiz Buchukuri, and this paper is published, of course, that under such conditions, that function f, the right-hand side, has limit when xt, function f, when the last variable is multiplied by t, and then t is sent to 0, it should converge to f0, not, I mean, as a continuous function on something else. It is sufficient that to converge it in h-1. So in this space of distributions, very weak convergence. We need this weak convergence, and another convergence which we need is this one for the flux functions. For the flux functions, actually we require the weak derivative. But it is understandable. I think it is easy to understand, because when these upper and lower phases come together, that the conditions, fluxes, must be very close to each other. And that's then this condition seems quite natural. And this limit also exists, not necessarily in space of continuous functions, but it is also weak limit. It's written here which kind of limit it is, and the result can be in h-½ So also not quite regular function, not complicated distributions, but still distributions. And the limit is distribution. Then the functional, which we had, the energy functional, converges to the functional written here. Functional 64. Functional 64 is the gamma limit of the energy functional. This is the result. The proof, as I told you, is about 5 pages. It is in the paper, and if somebody is interested, I can send this paper. The following Dirichlet boundary value problem is an equivalent. Now, we get energy functional now on the surface, mid-surface. But what kind of boundary value problem on the mid-surface corresponds to this energy functional? It's here. Boundary value problem 65 corresponds to the energy functional 64. So it's reformulated. So we can consider now that this boundary value problem 65 is the gamma limit of our original boundary value problem. And what is interesting here, we had conditions on the upper and lower surfaces, and the upper and lower surfaces disappeared. They become the area where the equation itself exists. There you cannot have conditions. But what is interesting, that this Q plus and minus, well, to be more precise, the weak derivative from formula 63 migrated in the right-hand side of equation. It went to the right-hand side of equation. Oh. No. Where we are, I cannot understand now. Yes, it went back. Why it went back? Yes. Variational. Well, complicated. So, extended divergence and so on. Oh, the jump was very.
The other way around.
Oh, no. No, I think I am wrong. I went back myself. Yes. Here. This is the energy functional which we get as a limit. And here is the boundary value problem, which is equivalent to this limit functional. And you see that the flux conditions migrated is the right-hand side. They stand in the right-hand side now. It's, I think, the most interesting in this gamma limit, that some functions migrate from one condition to the right-hand side to other conditions and so on. Now about a remark is here about these equations. And the remark says that it is remarkable that these conditions migrated. And let us comment on the weak derivative. If we why we call it weak derivative? If the function Q plus and minus will be extended in the domain continuously, extended from upper and lower domain, this what we get here by as a weak limit will be the usual limit. So that's why it's called weak limit. Yes. These flux conditions are really weak limit. Next, I want to explain you. Yes, when we get this equation on this surface, are they solvable, or they are not solvable uniquely? We investigated also this. We get Laplace-Beltrami equation. We will have the same result for the Lamé equation, the limit of Lamé equation, which is much more complicated. But in this case, it was much easier to prove that this obtained equation under certain boundary conditions is uniquely solvable. So we have this surface, we have corresponding boundary value problem. boundary value problem, and the anisotropic Laplace-Beltrami equation, the boundary value problem 66. And we can consider the solvability of this system, unique solvability. For this, what we need for this? For this, we need Lax-Milgram lemma. Yes, anisotropic Laplace-Beltrami equation with boundary condition, and well, anisotropic condition. Yes, anisotropic Laplace-Beltrami operator. And since it is positive definite, here helps the Lax-Milgram lemma. Here is about information about David Lax, which was a brilliant mathematician. I think he is still alive, and or not. I don't have the last information about him, but he was really a brilliant, or is a brilliant American mathematician of Hungarian origin. And much shorter was the life of Arthur Milgram, who died quite young, but contributed a lot also. If we have the bilinear form and positive definite, which is positive definite in the Hilbert space, and we have a functional also, then the equation AUV is equal to FV is uniquely solvable. That's the Lax-Milgram lemma. It is proved quite easily and is reduced just to the Riesz theorem about function, existence of functionals in Hilbert space. But in mathematical physics, it plays a tremendous role. Also in our problem, together with my doctor, well, Medea Tsava is not anymore the doctor student, and the another one just went to the school now. With these two girls, we proved that this operator, this equation is uniquely solvable, which we get. Okay, how to get the gamma limit? It depends how we scale what conditions we impose on the energy functional and how we scale it. Here is the demonstration in this last sector. Yes, sorry, again. Oh, Lax, Milgram, sorry. And here is the theorem about Lax-Milgram theorem was the first here, and Lax-Milgram theorem about the existence of the solution to this equation, bilinear form and the functional. U exists, the solution in Hilbert space exists, it's unique. And then we proved that this equation, which we obtained on the anisotropic Laplace-Beltrami equation under certain boundary conditions, is uniquely solvable. And the next is that exists another scale, different scalings, and different gamma limits. Theorem: suppose a scaled function, a scaled sequence, has finite bending energy. That is to say that distance to the orthogonal matrices 3 by 3 is integral, square integrable. If we have such condition, then the sequence is then pre-compact, and epsilon, and when epsilon is sent to 0, there exists a subsequence not relabeled, such that this limit exists, the limit 69, and completely different gamma limit occur here. If the sequence is functions have so-called finite bending energy. This result belongs to Friese, James, and Mueller, that if you suppose this condition 68, that the finite bending energy exists, and then make a scaling, then the limit exists, where is here the scale? Scaling is we have with epsilon square, as you see. Scaling is with epsilon square, then the limit exists. And the other scalings are not here possible. But the other scalings with other conditions are perhaps possible also. What is interesting here, the limit is quite regular. The limit here is in H1. It's surprising because the sequence is not such a smooth, but the limit comes out very smooth. The result of this is that the Wilmot's functional appears and so on. Okay, here I will stop for today. Thank you very much for your attention.
I think this mix-up is seen. Do you assume that it's always compact or maybe compact with boundary or without boundary? Is it important or not?
Repeat it, please.
This mid-surface must be compact or not, or must have some boundary or not. Perhaps it's not important.
I didn't understand, sorry. Maybe we will speak about it later. Sorry.
This mid-surface.
Yes.
Layer. This layer must have some boundary, empty or non-empty, should be compact, not compact. Maybe it's not important.
Compact or not compact, you mean this layer can be compact or not?
Yes, we don't.
Well, in this case, it's important.
Yes.
In this case, it's important, but perhaps one can consider, but it needs additional effort to consider the non-compact layers. But in practice, it's normally it's sufficient to consider the compact structures. Yeah, I don't know where you can apply the non-compact structures in this case, but mathematically, I understand it's interesting.
Okay, thank you. Very question, please.
Влад, можно вопрос на русском языке?
Да.
Вот там 59.
59
Да.
уравнение.
Там неравенство константы C1, C2, C3.
Я переключу, я не помню, какой там 59. Equation 59. Yes.
Да. 59.
Yes.
Вот эта константа C1, C2,
It's not equation, it's condition. Это условие.
Да.
Какие условия мы должны, what conditions we need to impose to that the gamma limit will exist. The first is this, it is convex. This functional is convex. And the second one is that it is, it has square estimate. These are conditions.
Они от эпсилон не зависят. Правильно? Константы C1, C2.
Константы не зависят, конечно, да, само собой. Иначе это не имело бы смысла. Это, по-моему, даже написано.
Да,
Yes. For some positive constants. not written that they are independent of this functions, of course.
N-мерного вы на N+1 перешли всю эту технологию.
Что?
У вас задача N-мерной, там, на N+1 всю достроили технологию.
Достроили.
Ну, спасибо. Вот это хорошее условие 50 лет. Да, спасибо.
Да.
Are there some other questions, please? Thank you very much again.
Thank you.
We have a quick 11:45.
Кого? Вот.
Спасибо. Merabi Babirgaro, so remote the most of our soldiers can not have us what to do. Or no, checking what others got into the so turn up like no other so it's international use. And we need more go. So now that's the next one on the list. Oh, now we will start with this topic of this period of the children. As the problem of the children will wait as a security. You are also one of the necessary. That's what I do.
Okay, let us start the next lecture of paintball surface from the exponents to parabolic collapse.
Thank you. Good morning, dear colleagues. Today will be the third part of our lecture, and I apologize if I boring you with this critical exponent every day. Today we will talk about Fujita type critical exponents on the unbounded domain, like half space, exterior domain, and yeah. Also, I apologize in advance. Today, I will also again show you the classical Fujita type results. We should start with this kind of problems. Yeah, maybe there is some new participants. I should repeat. In 1966, Hiroshi Fujita considered this kind of semilinear heat equation with non-negative initial data, and he proved these results. If P between this 1 and the 1 plus 2 divided by n, then there is no non-negative global in-time solution. By non-existence, here we mean that the solution will blow up in finite time. And for subcritical case, when P greater than this number, 1 plus 2 divided by n, then for sufficiently small initial data, there exists a global in-time positive solution. And also the critical case was left open in the Fujita's paper. Later, it was proved by Hayakawa in two-dimensional case and by this Japanese mathematicians also in 1977 for the multi-dimensional case. And they also show that for non-negative initial data, in the critical case, there is no global in-time non-negative solution. Yeah, and this number is called Fujita critical exponent. And today we will discuss about some extensions of this Fujita exponent on the half space and on the exterior domain, mainly on the outside of the ball. And in 1988, Mayer considered the same problem considered by Fujita on the k times half space. Here, Rk plus can be defined by this set. And yeah, Mayer was a PhD student of Howard Levine, as far as I know. And he proves that for this kind of set, the critical exponent in the sense of Fujita will be like this. 1 plus 2 divided by n plus k. Sure, if k goes to 0, then this set will be coincides with the whole Rn Euclidean space. Then this critical exponent will coincide with the classical Fujita critical exponent. And yeah, it was published in 1988, and in 1989. Katerina Bendel and Howard Levine, they consider on the same problem on the exterior domain with homogeneous exterior Dirichlet boundary condition on the boundary. And he proves that for this problem, Fujita critical exponent is still critical exponent. Here in the half space, it was a little bit changed. But here, the critical exponent will be the same with the whole Euclidean space and exterior domain. And in 2000, Levine and Chan, they consider the same problem, but with Neumann boundary conditions, with homogeneous Neumann boundary conditions. And in this case, they also prove that the critical exponent still will be the Fujita critical exponent. And later, Raoul, in 2011, he considered with Robin boundary condition. Here, alpha is a strictly positive number. Then he proves that also for the Robin problem, semilinear heat equation on the exterior domain has a critical exponent in the sense of Fujita with this form, the same Fujita critical exponent. And someone interested what will happen if in the boundary condition we will put some non-trivial function. Yeah. The first paper was by Katerina Bendel and Howard Levine and Keith Chan in 2000. They consider the semilinear heat equation, this one, with inhomogeneous exterior Neumann boundary condition, and also with inhomogeneous exterior Dirichlet boundary conditions. And in this case, they prove that there is the new critical exponent. It can be defined by this, n divided by n minus 2 if n started with 3. And in one-dimensional, two-dimensional case, the critical exponent will be infinite. It means that there is no any global in time solution for this problem, for Dirichlet and for Neumann also. And they prove that if P between this range and the boundary function satisfies this condition, the boundary integral of the f is strictly positive, then the solution will be blow up in finite time. There is no global in time solution. And if P greater than this number and started with three-dimensional case, then the problem has a global in time solution for sufficiently small initial data and a boundary function from this space. Here, if we consider inhomogeneous boundary conditions, the nature of the parabolic equation will be very close to the elliptic equation. For example, I forgot the year, probably in 1965, Serine considered the elliptic problem, this kind of elliptic problem. And he proves that the critical exponent of the elliptic problem will be this one. The same. And later, this result was improved by another authors, and they prove that there is also another exponent. This is for radial solution.
But the critical exponent was related to the time evolution. There is.
Yeah, there is. It means if P between this number, there is no any positive solution of this problem. Yeah, and if P greater than this number, there exists a positive solution of this semilinear elliptic equation. Probably it was 65 or 64. It was published in Acta Mathematica. Yeah, when we consider inhomogeneous boundary condition, if our boundary function depends only on the x variable, space variable, then the nature of the parabolic equation will be very close to the elliptic equation. Yeah, and recently in 2020, Japanese mathematician Ikeda with co-authors, they consider the same problem, almost the same problem with inhomogeneous Robin boundary condition. This is a parabolic equation, semilinear, outside of the ball. And here, a Robin boundary condition. Here also, boundary function depends only on the x. The parameter alpha is strictly positive. And he proves that if U0 locally integrable function and non-negative, if integrable function on the boundary, then the critical will be the same with the paper by Bendel, Levine, Jung. It means if P between this range, then if integral of the boundary function strictly positive, then the solution of the inhomogeneous Robin problem for the heat equation blow up in finite time. And also if P greater than this number, then there exists some positive global solution for some initial data sufficiently small and for some boundary function f. Okay, but here, if you mention is here, the critical case was left open. If you remember, when we started with the Fujita results, every results, the critical case was left open because critical case very quite difficult to prove. Because sometimes it can be belongs to the blow up class, and sometimes it can be belongs to the global existence part, and so it's the proof to prove the critical case quite difficult. And in this paper also they left open the critical case, and they also consider this kind of particular case when f non-negative and the initial function bounded from below this kind of polynomial. Here capital A is strictly positive, but the lambda is negative, but it bounded from below by this number 2 minus n. It depends on the dimension of the space. And for this kind of problems, he proves that if P between 1 and 1 minus 2 divided by lambda, then there is no global and time solution of the Robin problem for the semilinear heat equation. And also, if P greater than this number, then the problem have a global solution for some sufficiently small strictly positive boundary function. Yeah, in the both case, the critical case not investigated, and it was left open. And sure, using our yesterday's approach, logarithmic test function method, we will try to give answer to this question within this today's lecture. Okay, for this reason, let us consider the same problem with inhomogeneous boundary condition. Here, this boundary condition includes all three types of boundary conditions: Neumann, Dirichlet, and Robin also. Yeah, if beta equals to 0, we have a Dirichlet boundary condition. If alpha equals to 0, we have a Neumann boundary condition. If both of them strictly positive, then we have a Robin boundary condition. And let us formulate our first result. This result was published with my former PhD student Borukhanov recently in this year, Journal of Differential Equations. Yeah, suppose that this one is mistake. Initial function locally integrable, and f is also integrable function on the boundary. This is the same assumption with this paper. Here they also assume, here they also assume that U0 from L1 log and f from L1. Yeah, in this case, if boundary integral of f strictly positive and p equals to critical case, then our theorem states that there is no global and time positive weak solution of this problem. Yeah, sure. If alpha strictly positive and beta equal to 1, then our theorem completes the results by Ikeda with co-authors for the critical case. Okay, our approach was based also on the test function method with logarithmic argument. This method was developed in our papers. First, with this paper. Also, I present yesterday, published in 2012, 2022, sorry. And also in this paper, in the first two papers, we developed this method on the whole RN. First one was for pseudo-parabolic equation with forcing term. Second one was for quasi-linear heat equation with combined nonlinearities. Here, by combined nonlinearities, I mean this kind of nonlinearity. For example, ut minus u equals to here some parameter mu up plus here gradient nonlinearity. And in this paper was considered this kind of problem, also as a critical case only, and we prove non-existence results for this kind of equation. And also the paper 12 with Fino, Różański. In this paper, we develop our method or approach on the Heisenberg group, quasi-linear equations on the Heisenberg group. And they also obtained some results for the porous medium type equation with power law nonlinearity on the Heisenberg group. Yeah, and in this presentation, first time we will use this method on the exterior domain. We consider this kind of test function. Yeah, we will prove only for the Robin case, as another one will be the same, almost the same. Here we consider this kind of test function. Phi1 of t can be defined by this explicit form. Here L is a greater than this number, 2p divided by p minus 1. Oh, sorry. And second one, test function dependent on the x variable, phi to x, can be represented by this expression, h of x and xi of x. Here, xi of x can be represented by this logarithmic argument test function. And here we assume that the capital psi of S satisfies these properties, and it is equals to 0 on the range -1, 0, and it can be decreased on the interval 0, 1, and it's vanish on the if S started with 1. And the h of x here, this is a harmonic function. Define it on the exterior domain, and it satisfies this kind of problem. This function is a solution of this problem. This is a Laplace equation and a Robin boundary condition on the boundary. Yeah. Using this test function, we can multiply our equation by this function, and we can integrate by parts. And finally, we have this kind of integral identity. We call this definition weak solution, but some mathematicians call this very weak solution, because here there is no any smoothness of the solution. Everything only U. And sure, here we will use epsilon Young inequality to the right-hand side of this identity 6. Then for the first term, we have this inequality. Yeah, also here, this is almost the same with the first term of this integral identity. This is the same. And the second one depends only on the test function. And here also, we can estimate this term by these two terms. This is also the first term of the integral identity 6, and second one depends only on the test functions. Yeah, and if we put these calculations to the integral identity 6 here, then this part will be equals to 0. Yeah, because here 1 divided by 2, here 1 divided by 2, and it will be 0 equals to 0. And finally, the integral identity 6 can be written as this integral inequality 7. Here, our inequality does not depend only on the solution u. It depends only on the initial function, boundary function, and test functions. And here we need estimate these integrals I1 and I2. Here, capital C is a positive number. For integral I1, we have this kind of calculations. It's not difficult to get this one because we know explicit representation of the function depends, test function depends on the time here. Yeah, here. We can take derivative by time one times and put here, and we can change the variables. And finally, we have this one here, this C arbitrary positive constant. And here, capital T and the capital R, sufficiently large numbers. And with a similar way, we can estimate also integral I2. Here, Laplace operator. We also have some properties of this test function. Depends only on the x variable. This one, we can get the Laplace operator to this function, and using some properties. This is the functions with compact support, and the derivatives also will be bounded. Using these facts, we can also estimate this integral I2 by this expression here. C also arbitrary constant. This is capital T, and inside of this comma we have a logarithm. And yeah, we can put these calculations to the expression 7. Then we have this one. Here we have boundary function, and here initial function. And this part depends only on capital T and capital R. And instead of capital T, we can put some power of R, because both of them are sufficiently large numbers. Then if we assume that G are greater than 2, then the right-hand side of this R, all R will be the strictly negative. Yeah, here will be the negative. This is also negative. This is also negative. And here also R power minus G. And from here we can go to the limit when R goes to infinity. Then the right-hand side of this inequality goes to 0. This one also. It's why we don't assume any sign of initial function. Here, U0 will be some sign changing function also. Yeah, and from here we can get a contradiction, because in the theorem we assume that f in boundary integral of f strictly positive. This proof our theorem. And let us move next part. Yeah, here if someone consider the Dirichlet problem, then instead of this Robin harmonic function, we can put this Dirichlet harmonic function. This is also satisfies a Laplace equation. Also on the boundary, it will be equals to 0. For the case of Neumann problem, we can just put instead of h a constant, for example, 1, because the constant satisfies the Neumann problem. Laplace equation will be equals to 0, and on the boundary is also normal derivative will equals to 0. And repeating the same way, one can prove that, and the Dirichlet and the Neumann problem in the critical case has no global in time positive, weak solution. And next part, in the next part, we can consider the case when initial function bounded from below by some polynomial like this. Yeah. Here, lambda is negative number, satisfies this kind of properties. We assume that lambda satisfies this kind of restrictions in 3- and 4-dimensional case. We assume the same assumption with the paper Ikeda, but starting with 5-dimensional case, we assume that lambda also bounded from above by this 4 minus n. By these assumptions, if you consider a critical case, then semilinear heat equation with Robin boundary, and not only Robin, also with Dirichlet, with Neumann boundary conditions, does not admit global and time weak solution. And also, let us prove this theorem. Here we will use a little bit another method, not logarithmic dependent logarithmic argument test function. Yeah, also this results also completes the results from the paper Ikeda with co-authors for the critical case. Yeah, but unfortunately here, if dimension, where is this? Yeah, if dimension starts with 5, we still don't know what will be happens in the critical case, because our method cannot help to prove this result. And yeah, here these critical exponents grid this number. And let us prove this theorem. We consider almost the same approach, but here we consider radial test function. And here we suppose that this is equal to 1 inside of this ball with radius r, and it's decrease inside of this unknowns domain, and outside of this domain it will be equals to 0. And here also this is 0. We have explicit representation of function by t, and here h is also harmonic Robin function. Okay, and again we can multiply by this test function, integrating by part, and using the epsilon Young inequality to the right hand side. Finally, we have this kind of integral inequality. And we can put instead of p this number, because we considering only on the critical case. Then the right hand side of this, the last integral inequality, can be rewritten as this form. And for u0, yeah, here we don't have boundary function because this test function is non-negative, and we assume that also this boundary function is also non-negative. Then this integral can be estimated by 0 from below. And for U0, we have this one. Instead of this test function, we can write the explicit form. This is biharmonic Rauban function. And this is our test function. And we assume that U0 bounded from below by polynomial, this kind of. And if we estimate from below this integral, for example, on the unknowns domain, then this test function will be equals to 1. Because here we suppose that here it inside of the ball, it's equals to 1. Sorry. Yeah, and then we can explicitly calculate this integral, and it can be estimated from below by this expression. Here, capital A and alpha is a strictly positive constant. This is R power lambda plus n divided by n. This is this term strictly positive. And then we can put this this estimate here, and finally we have this one. Also here, instead of capital T, we can put R power G, and we have this one. Here A is strictly positive, and here C is also arbitrarily constant, positive constant. Then inside of comma, we have this R power minus lambda plus n divided by 2. And here we have this kind of terms. And let us assume that because in the theorem we assume that lambda is negative if n 3 and 4, and starting with 5-dimensional case, lambda bounded from above by this number 4 minus n. Then we can choose G like this, minimal value of these two numbers. And this one is strictly negative if lambda satisfies this kind of properties, and also this guy is also strictly negative. Then the set will be non-empty. Yeah, this set will be non-empty. Then we can go to limit when R goes to infinity, and then right-hand side of this last inequality 10 goes to 0. But in the theorem, we assume that A is strictly positive, and here we have a contradiction. It means that also in this case, the considered problem does not have global in-time solution. Yeah, now let us discuss about some open questions related with this kind of problems. In the same paper, Bendel, Levine, Jean, they also consider this kind of exterior problem. The problem which we discussed before, it was with inhomogeneous boundary condition. Here with homogeneous boundary condition, but with forcing term depending only on the x variable. And they also consider only Dirichlet case, and they prove that the critical exponent still this one. Yeah. And for subcritical case, if integral of this forcing term strictly positive, they have blow-up results for this problem. And for supercritical case, they have global existence results for sufficiently small forcing term and the initial data. But the critical case was left open, and this problem still open. And we hope that our approach will help us to prove this problem. Now we are working on this problem with our colleagues, our PhD students. And also there is open question related with this kind of restriction when the integral of fx equals to 0, but f is non-trivial function. Studying the critical exponent of this problem is also still open. And here Q can be equals to whole Euclidean space or exterior domain. And this is still open. For now, we don't have any approach how to prove this case. Also here, they consider only Dirichlet boundary condition. And so the Neumann and the Robin boundary problems for this problem 11 also does not investigate it. And also there is some interesting problem related to the second critical exponent, because here we have global existence only for sufficiently small initial data. But if this initial data and the forcing term quite large, then there will be the blow-up phenomenon for NAP. Then for this reason, it's interesting to study Lie type second critical exponent for this kind of problems also. And yeah, also one can study this kind of problem with here B some boundary condition. For example, Dirichlet, Neumann, or a Robin boundary condition. And if we assume that the boundary function f will be equals to 0, integral of f will be equals to 0 for non-trivial f, then this problem is still open. And also there is no any, for now, there is no any approach how to prove this kind of results. And also very difficult to study high order case because in whole Rn it's quite easy because we don't have boundary in Rn. And but if we consider, for example, this m power of Laplacian polyharmonic heat equation on the exterior domain, then this is also completely open for now. But on the whole Euclidean case, the critical exponent will be like this. If equal, sorry, first, if f 0, then the critical exponent will be like this. 1 plus 2 m divided by n. It was proved by Soviet mathematicians Galaktionov, Kurdyumov, Tikhonov, Samarsky. Sorry, Samarsky. Mikhailov. Sorry. In 83 or 84. Yeah. If we consider with inhomogeneous term, if f is not equals to 0, then the critical exponent will be like this. Critical exponent n divided by n minus 2m. here M is the power of the Laplacian. It means that there is no any global in time solution if n less than 2m. If n less than 2m, then the critical exponent will be infinite. But on the exterior domain, it's quite difficult to prove this kind of results because if you remember to the proof semilinear heat equation, we use explicit form of harmonic function, and for the m polyharmonic case, we don't know explicit form. It's quite difficult to find explicit form of this polyharmonic function, and very difficult to calculate this derivative, m times derivative. But recently we try, now it's still unfinished paper, we are trying to study a biharmonic case. Biharmonic case, now we considering with my PhD student Nordaulet Tobakhanov, this kind of problem. This is the same problem with Bendel, Levine, Chunk, but here we put a biharmonic operator. And we consider 6 types of boundary condition. This kind of Navier boundary condition. This is, we call Navier boundary condition if the function and its Laplace operator equals to 0 on the boundary. Also, Dirichlet type boundary condition, we say for the biharmonic operator, we say the Dirichlet boundary condition if it satisfies, if it's equals to 0, the function equals to 0, and also its normal derivative equals to 0 on the boundary. We call that this boundary condition is Dirichlet. And also there is another type of boundary conditions, for example, Neumann type boundary conditions. If normal derivative of this function equals to 0 on the boundary, and the Laplace operator is also equals to 0 on the boundary, we call this boundary condition a Neumann type boundary condition for the biharmonic operator. And there is also Dirichlet-Navier type boundary condition. This is if the function and the normal derivative of Laplace operator equals to 0 on the boundary, we call this condition Dirichlet-Navier. And also there is a Cutler-Sigillito boundary condition, and this kind of boundary condition. And the last six boundary condition, or a Neumann-Navier type boundary condition. This is like this. And for now, we have this kind of results. First, we studied a homogeneous case when f equals to 0. And if u0 satisfies this kind of condition, if the integral of u0 and the a of x non-negative, here a of x in the case of problem 1 and 6, this is a harmonic Dirichlet harmonic function. And in the case of problem 2 and 4, this is biharmonic Dirichlet function. Also in the case of problem 3 and 5, this is just constant. For example, it can be 1. Then all these problems admits no global in time positive, not positive, global in time weak solution if P between 1 and 1 plus 4 divided by n. But unfortunately, we don't have result about global existence because it depends on approach. If we try to reduce this problem to the integral equation, it's quite difficult to study properties of green function of this problem. And it's why we cannot investigate it for now, this result. We have here only blow-up result. And our next result about inhomogeneous case. Here we suppose that U0 locally integrable, F also locally integrable and locally integrable bounded function. And if F satisfies this property, if integral of F and A of X strictly positive, here also A of X, the same function as the previous theorem, then we have this kind of interesting results. In 1, 2, 3, 4-dimensional case, for all P, there is no global in time weak solution. But started with 5-dimensional case, there arise some critical exponent like this. And if P between 1 and this critical exponent and divided by n minus 4, then all of our problems from 1 to 6 don't have global in time positive, not positive, sorry, global in time weak solution. And if n started with 5-dimensional case and P greater than this number, then these all problems admits global stationary solution. Here by stationary, I mean the solution depends only on the X. For example, if we consider this problem, the solution of this problem also satisfies the semilinear heat equation. And then we can see that the heat equation has a stationary solution also. Here also our approach based on the investigation of elliptic problem first. We investigate this kind of biharmonic Poisson equation. If we remove this term, then it will be coincides with a biharmonic Poisson equation. We investigate this equation with these fixed boundary conditions, and for some sufficiently small strictly positive f, we can show that if p greater than this number and divided by n minus 4, then there is some positive solution of this problem with this kind of 6 type of boundary conditions. It means that our problem also have stationary solution for p greater than this number. Then using the comparison principle, we can get that the solution of problem xt, yeah, sorry, let me write another. V will be less than V of X for all time. Yeah, it means that our solution is bounded for all time from above. Then we can see that our problem has a global in time solution for some sufficiently small f and u0. Here, u0 will coincide with the function v, elliptic solution of elliptic problem. And yeah, and the last part, this is also related with open question. When we just start today's talk, we mentioned the paper by Mayer. He considered this semilinear elliptic equation on the half space, k times half space for this kind of, and he proves that the critical exponent can be defined by this number, and yeah, there is some open questions related to this problem also in the half space. For example, if we replace u power p by u power p plus f of x, with forcing term. Yeah. Then this problem is still open also. Recently in 2021, Agrawal, Jaleli, and Samet, they studied the case when k equals to 0, equals to 1. And they have that they studied this kind of problem, ut minus Laplace u equals to u power p plus f of x on r n plus. And they prove that the critical exponent of this problem will be n plus 1 divided by n minus 1. In the whole Euclidean space, the critical exponent was like this, n divided by n minus 2. But in the half space, it can be defined by this one. And here also, only one-dimensional case have infinite critical exponent. But started with two-dimensional case, there is a critical exponent defined by this expression. They prove global existence, also blow-up results. But for this kind of k times half space, it was not investigated, and still it's also open. And also one can consider the high order case. High order case also in this situation very difficult, because to prove this results, these guys, Agrawal, Jaleli, Samet, they use also some explicit representation of harmonic function on the half space. But if we consider this kind of k times half space, the form of this harmonic function will be quite difficult, and you need to calculate very complete calculations. And yeah, it was just a few of these open problems. There is still a lot of open questions. And if some students or some colleagues interested, welcome, we can investigate. Maybe someone will, someone now, some new approach. Yeah, this direction is still developing. Yeah. It was the last presentation. Thank you for your attention. If you have any question or comments, welcome.
Unless I overlook something when considering Rotan problem,
Yeah.
you always have positive coefficients.
Yeah.
The exterior, the attractive.
Yeah.
Is there something known for the opposite side?
Negative part, you mean? Yeah. Because it's even very difficult when you consider linear problem. Yeah, because there arise some problem related with Stiklov problem. Yeah, even if you consider a harmonic function. Yeah. For now, no, there is no such kind of investigations.
Another question, the proof you showed us about the exterior of the ball, there the symmetry played a very significant role. Do you expect that it extends, say, to exterior of a bounded convex domain?
Yeah, I think it's possible. It's possible. Because this Jan, Ben, Levine, Jan, they assume that this exterior domain can be bounded from above and below some ball. Yeah. Thank you.
In relation to Day3, you have statement that the global solution exists for some functions f and q0.
Yeah, sure.
Can you somehow characterize the class of this f and q0 or it just know some examples?
Yeah, we can choose some functions from this space, yeah, and we can investigate this kind of elliptic problem. And using a radial function method, we can, for example, we can search the solution in this form, minus m some positive number. We can put this one here and get calculation. Then for this kind of p, we can show that this function will be the super solution of this problem. It means that this is also super solution of our problem. Then using the comparison principle, we can conclude that our solution is bounded from above for all t.
Okay, but why are you saying for some f?
For some f, you mean? Yeah, because we cannot choose any arbitrary.
Okay.
Yeah, there exists some f, u, such that the solution can be exist globally. For not all any
Not
f.
all.
Yeah.
Thank you very much again.
Thank you.
So the session is over. The afternoon session will start at 3 p.m.
Operator on manifolds in the morning and on the Laplace-Beltrami version. In particular, if we want to work with a Laplace operator on S2 here, we need the corresponding version here, the Laplace-Beltrami part of it, when we compute the Laplace operator in these spherical coordinates as done here, as it is very often a classical exercise for students to compute the Laplace operator in this polar coordinates. Okay, from this one can also immediately get the dimension of the corresponding spaces. You see the space of homogeneous polynomials of a certain degree is very large, quadratic, and the space dimension of the harmonic polynomials is 2n+1. If you compare it with the periodic setting on the torus can be seen, the one-dimensional torus can be seen also as a S1. We are here on the S2. The torus is more or less a S1. And there the harmonic functions of degree n on the torus are sine nx and cosine nx. There the dimension of the harmonic polynomials on the S1 is 2, and here the dimension is 2n+1. Okay, to go further, we need again the Legendre polynomials. The Legendre polynomials were already some example, some topic from yesterday, but because the Legendre polynomials play here a very fundamental role in the following considerations, let's repeat the things here again. That means, oops, now he is faster than I do nothing. Okay, we were here, and we can here give the definition that the Legendre polynomials are uniquely determined by 3 conditions. They are polynomial of degree n. They are orthogonal to each other with respect to the Legendre inner product. That was already the Jacobi case from yesterday, where the Jacobi parameters alpha and beta are equal to 0. And here we take the normalization. If we take the capital P, means here's a normalization that at point 1, we normalize these polynomials at 1. Clearly, if we absolutely start with this definition, there's one problem. It is not clear at all that these polynomials really have no zero at the point 1. That means if we take this as a definition of these polynomials in such a way, we need in principle a lemma before to say that these Legendre polynomials have only zeros in the open interval -1, 1, that this definition here makes sense. Okay, but we can escape from this by giving some more equivalent definitions. One equivalent definition, namely, is the Rodriguez formula. And this Rodriguez formula is also very nice because one could also use it for a typical exercise in an analysis lecture, because from this formula to take the nth derivative of a polynomial of degree 2n, namely the polynomial of degree 2n is 1 minus t squared minus 1 to the n. It has an n-fold 0 at -1 and another one n-fold 0 at +1. And if you start to differentiate, if you differentiate once, then you have n-1 zeros at plus and -1 and 1 0 in between. And now you go on and differentiate, and every time you use Rolle's theorem. And with Rolle's theorem, you get after n differentiations that you have n simple roots in the open interval -1, 1. And that's the polynomial of degree n. It has only n zeros. Therefore, from this formula, it is very easily seen that these Legendre polynomials have n simple roots in -1, 1. And this means it has no root at +1 at all. Okay, now we have the three-term recurrence relation. If you define it by P0 and P1 and the corresponding recursive relation of this kind, you can compute in this way every following Pn plus 1 if you know Pn and if you know Pn minus 1. Very important relation. And you have also these polynomials as a solution, as one of the two solutions of the Legendre differential equation. This differential equation has two solutions, one bounded and one unbounded solution, and the polynomial one is lead to these Legendre polynomials. And last not least, we have the explicit representation, which is clearly also very interesting to sort these polynomials, these Legendre polynomials by monomials. But be careful, never use this formula here for your computations. Because if you put this into the computer and you take n larger than 10, then you are totally lost with such a monomial representation. You have a lot of instability involved. That means that's the worst one could do with these polynomials. If you want to work with these polynomials of high degree, then please use the three-term recurrence relation. All fast algorithms with Legendre polynomials, if you want to work with polynomials of degree 100 or even 2000, then you have to define these polynomials by the three-term recurrence relation, the only way to work in a stable way with these polynomials. Okay, here's one result, one important function. Here is a generating function for these Legendre polynomials. This reciprocal of a square root is represented in terms of Legendre polynomials as this infinite series. This is, leads also to another important corollary, namely the Poisson kernel, which one could use very often as an example for a nice localized function. It's a very nicely localized function. If you look on this right-hand side here, you immediately see that this is very much localized at 1. Insofar, this is then also a good ingredient to construct localized functions on the sphere. This Poisson kernel is there very important. Okay, the Legendre polynomials itself are unfortunately not sufficient to define our polynomials on the sphere. We also need the so-called associated Legendre functions. They are very much related to the Legendre polynomials, namely we take case derivatives of the Legendre polynomial Pn here in this way, and we multiply it again by 1 minus t squared to the power of k over 2 and with some normalization factor. These functions are called associated Legendre functions, which are in this representation not every time real polynomials, because you take a certain square root of 1 minus t squared there. If you rewrite these polynomials in theta and rho in the angles, then 1 minus t squared would be 1 minus cosine squared would be sine squared, and then that means it's sine to the power of k, but it's then not a polynomial in this representation here. But for even k, you really have a polynomial, and you have also an different possibilities of characterization of these associated Legendre polynomials. Again, here the definition by the derivatives using the Rodriguez formula for Legendre polynomials itself. We have the recursive representation. Again, let me emphasize, if you want to make computations with these functions, you have to use this recursive representation. The only possibility to get them in a stable way for, let's say, n and k around 100, don't use any other formula which I show you here. And again, it's a solution of the general Legendre differential equation. In this way, you get these associated Legendre polynomials as solution. And again, you have the explicit representation in monomials, which is more or less only somehow to complete the representation. In principle, we will never use such a formula in monomial representation. And we have some orthogonality as well, that for fixed k, for fixed upper index k, you have here such an orthogonality between the lower indices m and n, that on the right-hand side you have Kronecker delta of m and n. That means this orthogonality is very important later on to get orthogonal basis of polynomials and to understand orthogonality on the sphere. This result will be used heavily there. And you need a couple of lines of proof to show by induction this formula. It's a lot of technique involved to prove it. Okay, now we come to spherical harmonics, and we define these functions here r to the n in general for the whole three-dimensional space times these associated Legendre functions, where we want to include also negative k, and we defined it only for positive k. Therefore, we have to take the absolute value of k of cosine theta, and then the trigonometric part e to the I k rho comes in. And if one makes a corresponding computation, one can show these are harmonic functions on R3. That means harmonic homogeneous polynomials on R3. And let me also mention that from now on we will use both notation, the notation where we have here two angles and the notation where we have here an x value from R3, that we identify both notations and do not differ with the functions which are behind it. Okay, now we can also look into the corresponding definition of the harmonic functions on the sphere. That means we say Hn, that will be for the rest of the talk here, the important definition, the harmonic functions on the sphere S2. These are the restriction of the harmonic functions of the harmonic homogeneous polynomials on R3 restricted to the sphere S2. That is by definition here. And functions Yn is given on the slide before, belonging to the space Hn of functions on S2 will be called spherical harmonics of degree n. That is the main definition of our polynomials, and we immediately get the space dimension of Hn, that is again 2n plus 1. That is somehow the main part which we need here for understanding our main ingredients, the polynomials. Okay, now we want to have for this space an orthonormal basis. That means for this atom of harmonic and homogeneous polynomials of exactly of degree n. Please have in mind this on the torus, that would mean we discuss only e to the inx and e to the minus inx, the two-dimensional space. Here it is a space of dimension 2n plus 1, which we discuss here. And again, these functions where small r is equal to 1, these functions here, these spherical harmonics given in this way, they are an orthonormal basis. They build an orthonormal basis for this space of harmonic functions where k runs from minus n to plus n. Now, k runs from minus n to plus n gives the 2n plus 1 different elements in the space of dimension 2n plus 1. And note also here one difficulty, that clearly these two factors are somehow connected. The k in the e to the ik rho factor also appears here in this way. That means you cannot easily simplify by making a tensor product in some way out of it. These factors are belonging somehow together. But from now on, we have an orthonormal basis in this space of harmonic polynomials. Okay, here are some pictures. Important one to say in this way, writing it with exponential e to the ik rho, these are clearly non-real functions. And insofar I say here, I plot here the real part. Clearly, they have also an imaginary part. In some literature, instead of these functions, one discusses the cosine and sine versions. But I think in most literature, one goes with the exponentials e to the ik rho factors, and then one has basis elements which by themselves are already non-real functions. And as you expect, if n becomes larger, here n is 15 and 31, then it becomes more and more oscillating on the sphere, as can be seen from these two pictures. Okay, now you immediately also can emphasize that we have orthogonality between the two harmonic spaces Hn and Hm when n is non-equal to m. That means we write our inner product in terms of d rho and d theta with this polar coordinates, and then you compute the inner product between these functions. Please remember this were factors of some e to the ik power and of some associated Legendre polynomials. And it could be if the different k's are different, then already the inner integral is 0, and then it's very easy. But if you have the same k, then you have to go on to use the orthogonality of the associated Legendre polynomials to show that Hm is orthogonal to Hm. Let's summarize at this point. We have now an orthogonal decomposition of our polynomial spaces into these harmonic spaces Hn, which span then the whole polynomial space. And next part, we want to compute such a sum here. You already know from our talk yesterday that we see this as a shift of the directly kernel, more or less, of the sum of the y and k. We shifted by xi, and this is clearly a building block for our shift invariant basis, and we want to know what comes out. And the famous addition theorem says this is nothing else than the Legendre polynomial Pn. It's the inner product of xi times eta, a very important formula that we can rewrite such a sum, which gives us the localization, can be described as Pn of xi times eta. So we understand the localization of the Legendre polynomials Pn very well. They are very large at 1 and very small far away from 1. That means this sum on the left-hand side is very large if xi and eta are very nearby, because then their inner product equals to 1 somehow. Now, this is a very rough idea how to why we have here localized functions. Okay, we will call this left-hand side or even the right-hand side here as reproducing kernel for the corresponding Hilbert space of polynomials. It is a well-known name for it, and we can go on to get some results out of it. For instance, one corollary from the theorem, which immediately follows from the addition theorem, is if you integrate f against this reproducing kernel, you get back the function f if f is from this harmonic space Hn. This is clearly also very important for us to have this reproducing property this way. And because it's so important here, a two-line proof, we write f from the harmonic space as a Fourier series in this finite dimensional space, finite dimension of degree 2n plus 1 in this way. Then we plug it into the inner product, we get this double sum, and then we have the integral over two spherical harmonics. Spherical harmonics yield an orthonormal basis for the space. Therefore, this inner product, this integral is only non-zero if k is equal L. That means the inner sum with L disappears. It's only one sum of k. Again, because f itself is this function, you get again back the function f at point eta. This is a classical Hilbert space theory and reproducing kernel Hilbert spaces, a very general theory behind, and here one nice application for our polynomial spaces. Okay, now we can represent an arbitrary polynomial of degree n as a sum of its atoms in these harmonic spaces Hn, this orthogonal sum of these harmonic spaces Hn, and these gives all polynomials, which is not trivial to prove. That means that we really get all polynomials on the sphere. One basic ingredient to prove it is this formula that one can represent an arbitrary polynomial of degree n on the sphere as a direct sum of a homogeneous polynomial of degree n and another homogeneous polynomial of degree n minus 1. But then you to prove this and the corresponding results for the harmonic versions need a couple of steps, which I want to omit here, only to give you the impression that one has to work here at this point to prove it. But if we have such a representation, then we have now approximation theory behind, because we know from classical Weierstrass results that polynomials are dense in the corresponding spaces. That means now we can approximate arbitrary functions on the sphere with our harmonic functions. That means taking an arbitrary function f from the Hilbert space, we can approximate it as good as we want by functions from these harmonic spaces Hn. If we sum up these harmonic spaces up to a certain degree, capital N, and we have to take capital N big enough. Okay, now that means we immediately also obtain the dimension of the polynomial space of degree capital N on the sphere. Namely, we have only to sum up the corresponding finite dimensions of the harmonic polynomial spaces. And this gives us capital N plus 1 squared as a full dimension of polynomials of degree N on the two-dimensional sphere. If you go to higher dimensions, then the square goes on also to 3, 4, 5, and so on. There are corresponding formulas. All what I have done up to now here can be also more or less easily generalized to higher dimensional spheres. And there's one famous monograph which covers this theory. That is a lecture notes book from Müller from Aachen, who published this in the 70s of the last century, and more or less the whole analysis of such spherical harmonics is very well described in this basic book. Okay, now the topic here in this talk is some multiscale decomposition. That means we want to put here some scaling spaces into the game, and let's write them here new to the J, which should be also a Vj, but to distinguish them a little bit from the talks yesterday and the day before yesterday, let's take this calligraphic version of the space Vj, and we only do it here in a dyadic way. That means the whole space of polynomials of certain degree, 2 to the j minus 1, which is nothing else than this orthogonal sum of harmonic polynomial spaces will be considered. We have immediately the embedding. We have a chain of spaces in this way. And as I said, that they cover all polynomials, the closure of all these spaces in Uj with respect to the Hilbert space norm gives the whole Hilbert space L2 of S2. And we call this a multiscale decomposition of L2 of S2. And again, let me say here, we have now basis for these spaces. Very well. That means we could close here. We have orthogonal basis of spherical harmonics, and we are done. But our basis elements Y and K, which I showed you, where I showed you pictures, they are in some sense totally frequency localized. They belong to some frequency N and K, and they are the orthogonal element belonging to this one frequency. That means we have the, in frequency sense, we have the best possible, best localized basis we want to have. That means stop, it's the end. But now we want to have the mixture. These best localized frequency basis is totally badly localized in space. A sine function, a cosine function, it oscillates over the whole interval. There's totally no space localization. That means now we want to use the machinery from yesterday and the day before yesterday to get again a mixture. We want to have now time localized bases of these spherical harmonics, of polynomial spaces which are somehow localized on the sphere. And clearly, by this way, if we get more basis elements which are localized on the space, on the sphere, we lose localization on frequency. Now that is clear, and now we look to try to get other bases. Therefore, we want to have also a discretized version. Now in the community of time frequency analysis or Fourier analysis, people now distinguish, or people can be distinguished in two groups. The one group is going on and to make it continuously, to say I move one function continuously around and have somehow a continuous time frequency analysis. And I'm more in the other group where we want to discretize it, and we want to move one function to other points only in a discrete way, to some discrete number of points, to get some basis and to get some discrete frames. That means some people also discuss continuous frames. We want to discuss discrete frames with a discrete number of elements in the frame then. Therefore, we need now some set of points, and therefore we take this point set nj. On the j's level, we take these points, about 8 times more of points than the dimension of the corresponding space. That means in the beginning now, we take here the more easy part. We go for frames to handle with, and we include the North and the South Pole into this set nj of points. That means regarding our angles theta and rho, we have somehow an equidistant grid, which clearly mean if we take this grid on the sphere, it's not anymore equidistant, because anyhow on the sphere up to the 5 regular polytopes, there is no equidistant point system on the sphere. Therefore, we take the easy part to take an equidistant system with respect to our angles. And then we have such a nested system of points. Nested is clearly very nice from an algorithmic point of view. The old points can be used again for the new points. And also one can easily see that corresponding discrete function sets are nested in some way. Okay, here's a picture where you see from level 3 and 4, if you look from the North Pole onto the sphere, how these points are located. They are somehow equidistantly of circles parallel to the equator, and you have a lot of points near the poles and less points near the parallels on the equator. Okay, and now we repeat the whole business from yesterday and the day before yesterday. We want to have scaling functions phi j, and we want to localize them around some points xi, lm from our discrete set. And clearly, you never expected something else. We have here the shifts in this inner sum, and then we sum up over all harmonic spaces. And these are is the corresponding representation of such a scaling function, which is localized. And because of the addition formula, you know, we can simplify it. In principle, the inner sum here is nothing else than the Legendre polynomial at this point x times the discrete point psi lm. This is a definition here. With these functions, we can work nicely. And we have immediately now some properties of these functions. This goes back to the work of Daniel Potts, Gabi Steidl, and Manfred Tasche from 1996. We take xi, points xi from this discrete grid nj, and we have different properties, namely the integration of an arbitrary function from the scaling space with respect to phi j gives you the function back itself. Let's mention the equality here. We only get if we take polynomials itself. That means now it means f is again from this space Vj. For polynomial, we have here real equality. If you more look into the approximation theory, and if you say you take an arbitrary function from L2, then you have more or less here up to a certain approximation order, somehow also this formula. But clearly for an arbitrary L2 function, you do not have equality there. Okay, and you have here some normalization, the L2 normalization, and the pointwise evaluation of such functions, which show again that you have very highly localized function. Why it is clear? That means the function itself, if you integrate over the whole sphere, then the L2 norm is 1. And if you take phi j at this 1 here, then you get a very large number. That means you have very nicely localized functions phi j. Okay, and here again, on the last slide, I said very nicely localized. And now comes the exact version of what I mean with localization here. We ask for the minimum of the L2 norm of all functions from this polynomial space Vj, with a condition that at a fixed point it has a value 1. And now we want to find the minimum of all L2 norms. It's given by this function phi j with a right normalization in this way. Okay, we have again that the span of all this phi j really needs a corresponding space Vj. But please note, we have here around 8 times more functions in it. It is not a basis. It is only that the span yields the space. It fills the whole space, but we are in the framework of a frame here. That it's not a basis here. And the good thing here, it's a tight frame. Tight frame means yesterday we said if we have a frame, then we have A times something is less than the sum of the squares of the frame coefficients is less or equal B times something. And here A is equal to B. We have here really the version that we have a tight frame, which is computationally very, very good. Because if you have a tight frame, then it's also, you know, the dual frame. And the dual frame you need in principle to compute the frame coefficients. That means, therefore, this is a very comfortable situation to have a tight frame at this way. Therefore, these function systems can be used very nicely. And again, here, some normalization if you integrate the function phi j here by itself, only shifted to the function psi j Lm, you get every time the same value. Here you see these localized basis elements. If we take as a point Xi Lm the North Pole, that means then clearly it is localized around the North Pole. The one is phi j and the other one is phi 5. You see already very nicely localized functions on the North Pole, which you can rotate now to the other points, which you can do, for instance, also by some algorithms with Wigner functions, but you can use here also the corresponding algorithms for associated Legendre polynomials that works very fast to work with such basis elements. Clearly, you lose frequency localization. If you include space localization, you lose frequency localization. Okay, then we clearly want to have some wavelet space. And as wavelet space, we take here all frequencies, all harmonic spaces Hn from 2 to the j minus 1 to 2 to the j minus 1. That means clearly a large space in our wavelet space, more or less 2 to the j different harmonic spaces. And you can compute the dimension here. It's somehow 4 to the j in some way, 3 times of it is a dimension of this wavelet space. And again, the wavelets fulfill all these nice properties, which we could include here. We know about the shift by functions psi. We have this definition of the psi j. We define it in this way with some points psi j plus 1 here. We have such a formula. This is in Wj. And these are points from the point set of level j plus 1. Okay, and this again can be written in a more easier way with the Legendre polynomials. And we have more properties, again, going back to this paper by Pott, Steidl, and Tasche. We have a reproducing property again. We have orthogonality with respect to the scaling space before. This is very easy because we split our different, we do not overlap the same harmonic spaces. That means everything is split into different harmonic spaces. Therefore, this orthogonality between the scaling space and the wavelet space is easily seen. And we have the normalization again, and we have the localization. If we ask for the best possible best localized wavelet in the wavelet space, then we have the same answer. Yes, our functions do it, which we have defined. They give, in this sense, the best localization. And they span also the corresponding wavelet space. Again, we do not have a basis. We have a frame with an oversampling of a factor 8 about. And we have also a type frame in these spaces Wj, giving in this way that the L2 norm of the function f can be described by some weighted norm of frame coefficients. I do not go into the details to describe these coefficients, key L here. They have to be computed in an extra way to get this tight frame version. And you have again that the typical wavelet assumption, these are wavelets of higher degree. And also it happens here as it happens for all wavelets in the world, that the integral is 0. Integral of wavelets is 0 because you do not have polynomial of degree 0 involved. You have only higher oscillating parts involved, and then the integral is 0. And here, let me mention that this is not the Parseval equality. That's a frame equality which gives a tight frame. We have no basis here. So I put it for myself here in red again, not to remember that this does not mean we have a basis here. Okay, here again, the wavelets, you see a little bit distinguish them from the scaling functions. They have also negative parts. If you integrate here, you have an integral 0 for these wavelets psi4 and psi5. Therefore, they look a little bit different, but they look localized. Okay, now we switch from the frame system to the basis system. That was mainly work of one of my PhD students, Noemi Lein-Fernandez, who looked into this. Can we take this frame construction from Potts, Tasche, and Steidl to remove a lot of elements to sort out to get a basis of this polynomial spaces. And in some sense, she was successful to getting it. Here's the corresponding discrete set which we need for this purpose. Nj, and the B stands for basis here in red, to make it here in red, there's a difference to the set before. We look into these Cartesian grid of this kind, where we have here L and M in a given way. And here you see that we have now 2 to the 2j minus 2 many points. That's exactly the dimension of the corresponding space which we want to use. And to have really a basis, we need to include such an ugly value of aj to distinguish between the different spaces. Okay, and you see immediately the dimension of the space Vj was 2 to the 2j minus 2, and we have exactly as many points here. Here you see for level j equals 3 how the points look like. Again, on the rectangular of length 2 pi for the equatorial angle rho, and for of the length pi for the longitudinal angle theta. There it looks very nice. Clearly, if you project them back to the sphere, you have much more points near the poles than near the equator. Okay, again, let me compare this result with the corresponding wavelet result from Potts and Steidl. There we had this scaling function result. This was a result of Potts, Steidl, and Tasche for the frame system. Now we want to change it what remains if we restrict this to the basis. And that means the first three properties absolutely remain. If we restrict to less points Xj of this particular basis grid, then again we have the localization of these functions. We have this normalization. We have the reproduction property. This was the same as before for the frame. And now we have new properties, namely we have now again the span property, but now it's a basis. Now we have really linear independent functions in this way. And we have also a respaces, and what's written down here is a respaces property. It's not an orthogonal basis, therefore we do not have the Parseval equation here. We have res basis property with a left and a right inequality, which I replaced here by the similar symbol that we have here, a respaces. And again, we want now to construct also a wavelet basis. And here we switch a little bit into different spaces. This was very difficult. We worked very hard in this PhD project to get for these wavelet spaces basis. And we only got it in this particular system when we take it here from n+1 to 2n. In the frame paper from Potts, Steidl, and Tasche, it was from n to 2n-1. Small difference, but not too big difference. And again, here you could look at the dimension of this space Wn, and you need now a point system of so many points. And here it comes, this point system. Again, we have in the equatorial angle, we have here such equidistant system, 2m pi over 3n plus 2. But in the longitudinal way, we have to take some zeros of Legendre polynomials. We have to order this circles parallel to the equator. We have to sort them at the height of zeros of Legendre polynomials. And we have also to include here some AL, and then we get this point set. And here's a picture of this point set, how they look like for these fundamental systems for V4 and W4 in the sense to also to have such hierarchical system. And again, we have here the properties to compare it. Again, to write it down here, this is a frame part from Potts, Steidl, Tasche. What we can use as well, we now in the wavelet part, we have the reproduction property, it remains. We have the orthonormality, it remains. The localization remains. But here we have now the respaces property. And that, in this case, I really have to say this was a not so easy proof. It used a couple of pages in the PhD thesis to prove that this point system is really a respaces to show the orthogonality there to the other spaces. And at this point, I wanted to come to an end with frames and bases. And now I want to switch a little bit to uncertainty principles on sphere, because this we want to highlight a little bit more on localization, how we can describe the localization between time and frequency. On the one hand, we split it into polynomial boxes somehow. There we have also some frequency localization by hand, by saying our frequency part of the function is localized in some interval. And we discussed also now what we can do with time localization. And one possible point of view is to go in the direction of the Heisenberg uncertainty principle and to put this onto the sphere and to look how much our functions are localized in this way. And there was a lot of work done by people trying to understand the Heisenberg uncertainty principle, which is known from the Euclidean case on the real line and on the n-dimensional Euclidean space, how one can construct such Heisenberg principles on the torus and on the sphere. And here's one way how one could do it on the sphere. One could introduce a variance in space. I do not have time to give you more explanation in a geographical or in the geometrical way. In principle, you ask here how the mass of a function is involved in some cap around some point, and you can measure it in this way. And the same, you can look for variance in frequency. That means if you want to have small variance in frequency, you want to have more or less only a very small number of Fourier coefficients f hat here involved. And this comes into picture by taking the square root of the Laplace-Beltrami operator in this way. Then you have here this k times k plus 1. I do not want to give a possible introduction of these formulas. Please take these two variances. They describe the localization in space, variance in space, and they describe the localization in frequency by a certain way. Then there's a paper from Narkovich and Ward from College Station from '96. They showed that if the space variance of f is non-zero, which includes the constant functions. The constant functions will give a product 0 times infinity or infinity times 0. You cannot include them in such an inequality. But for all other functions on this Hilbert space L2, or to avoid infinity, let's say 2 times differentiable functions on the sphere, you can say that this Heisenberg product here on the sphere is greater than 1. That's an uncertainty product. You cannot get better localization both in time and frequency. In principle, you want to have for both factors 0, but this is totally impossible. This product is every time bigger than 1, and one can produce examples where this bound is best possible. For the Heisenberg principle, one knows very well the best possible, the best localized functions. These are the Gaussians. The Gaussians are produce on the Euclidean Heisenberg principle the equality sign. But have a look here. Here's a greater 1. The greater 1 shows already that probably there will be not optimal functions because we have here a greater 1 and the bound is best possible. That means there is no optimal function in this way. Nevertheless, one can look into the functions which yield somehow this infimum 1 by some limit. And here is one class of functions, the Gauss kernels, given in this way by some power of E, and one can construct the corresponding space variance and the corresponding frequency variance by some tangents hyperbolicus of some parameter lambda. Lambda must be greater than 0, but if you ask for lambda to infinity, then this comes out, and then it's an easy L'Hopital computation to show that then you get a 1. But for lambda equal infinity, you do not have an L2 function. That means that there's only a theoretical limit you get. And there's also another possibility to do the same with the Gauss-Weierstrass kernel. A paper from Rösler and Voigt discussed these kernels in detail, and they also showed that you would get with this parameter rho to 0, you would get here also such best localized functions in the sense of this uncertainty product. Okay, that means we want to look for our functions which we have and want to understand in which sense they are optimal. And okay, that means now we want to restrict to polynomials. So the topic of this lectures here, we want to discuss polynomials. And insofar, we want to minimize on a finite dimensional space. There I really can write a minimum over all polynomials to write down for this uncertainty product. What is it? And the same for all wavelets, trigonometry, or for all polynomial wavelets here. If you take the minimum of these functions, what do you get? Clearly, you cannot get one. You get some number bigger than one, and it's clearly interesting which number would you get. Unfortunately, up to now, there's no chance to solve this nonlinear problem. A lot of people working on it, also on the torus and on other settings. This is highly nonlinear, and up to now, no one sees a chance to compute this minimum, which would be very nice to know. But one can ask for the best space optimal spherical harmonics from our set. That means the task would be what happens if you want to optimize the space variance minimum here if f is from some scaling space Vn. And here's the answer, which is also going back to my PhD student, Noemi Lein-Fernandez, that you take some first zero of the Legendre polynomial, then this minimum of this variance is given by this way. And then you know also the best possible scaling function of this way. This can be given in this way. In the denominator, it's only a normalization factor. And here in the numerator, you get again this polynomial with these Legendre polynomials and this normalization here. That means this part is easily solvable. And let's have a look on it. Here's some numerical computation. Have a look. This is a corresponding variance of this functions that becomes very small, clearly. But if you look at the frequency variance here, it becomes then very large of this function in this way. And then what happens with a full uncertainty product? The full uncertainty product somehow convergent to some value 1.1 and so ever. That means we do not solve the nonlinear problem. The nonlinear problem is unsolved. What is the minimum? What is the real minimum over the whole product of time, space, and frequency localization? But if you restrict your problem to optimize under all polynomials the space localization, then here's the answer, which functions will do it. But you see, you need to define your own type of localization, and you get different answers. 10 slides before, I said the best possible localized functions are these ones. Now I have other functions which are best localized. It depends which is your localization criteria to say what is the best one. Okay, my time is over, but let's say again on the last 2-3 slides, the same can be done for the wavelets. Now we are in the wavelets, and here you see this uncertainty product in terms of Fourier coefficients. If you write down it in terms of Fourier coefficients, then this is this ugly product of different numerators and denominators. And I think you see there's no chance to optimize this over arbitrary sets of CK to find the minimum. But again, you can, yes, again, an example of the Dirichlet kernel. If you take the Dirichlet kernel, then you end up with an uncertainty product which grows like square root of n. That means Dirichlet kernel is clearly not a good option. Here's the corresponding picture, the corresponding Dirichlet kernel. It's not so much localized in time. If you take here the corresponding coefficients in front of the Legendre polynomials as 1. Not a good example. Let's make better examples. Here's the answer. Again, we need now zeros of associated Legendre polynomials to define the corresponding optimal function. Here's the optimal function, again, written as a Fourier series representation in this way. And the variance is then again given by this number of the corresponding values of the first zero of the associated Legendre polynomial. And here is again the computation. We have a nice time localization, space localization. It becomes smaller and smaller and smaller, but the frequency localization of these wavelets becomes then very large, and the product goes to some value of 4 point something, clearly much larger than 1. And here are some pictures of these localized, best localized functions. Here you see really nicely localized in space, localized on the North Pole. You lose localization and frequency. And I apologize for overdue my time. Thank you very much.
Thank you very much for your lecture. Are there some questions or comments?
Did you ever consider make it sense to consider the frame operator connected to your frames? Calculate something like spectral or so?
Yeah, we know the corresponding frame bounds, no? And because we have tight frames, life is easy. We can compute. We have formulas for the frame coefficients, and we have also algorithms. In particular, Daniel Potts and his group, they have full fast algorithms for all this. Now, I didn't went into the question of fast algorithms. They have also the polynomial fast Fourier transform algorithm for spherical harmonics. It means all what I have said here can be immediately and nicely put into algorithmic computations. If you want to do some computations, you find on the homepage of Daniel Potts in Chemnitz, you find corresponding fast algorithms to handle some stuff of this kind. Yeah, these pictures which I have shown here are produced by MATLAB. No? And also previous pictures which I had in my previous talks, most of them are produced by Mathematica, by this Wolfram research program Mathematica, because this works symbolically and it's very easy. I think the spherical harmonics which I showed today, there we have some MATLAB code, which is also publicly available from my homepage, that you can download there, the MATLAB code to work with it.
Thank you very much again.
Yeah, thank you.
Yeah, it's 16:45.
Okay. Good morning, everybody. Today is the set lecture devoted to the asymptotic analysis of system with a small perturbation. We will consider KdV equation, Korteweg-de Vries equation, and this equation is very popular for different studies, and a lot of problems were studied for this equation. As maybe you know, that this equation appear in connection with the attempts of mathematical description of solitary waves. Solitary wave was discovered by John Scott Russell in 1834 years. In 1834, he prepared a paper describing this phenomena and sent his to a journal, but paper did not publish because people said it is impossible. Later, John Scott Russell prolonged to study this phenomena. He studied different properties of solitary wave, prepare another paper, and this new paper was studied after 9 years after discovery by him of new phenomena. So after a lot big discussion of this problem, because this kind of waves was not included in current models of hydrodynamics, and some equations were proposed for description of this phenomena. A first of this description was proposed by Businesq seems to me, in 1874, and later in 1895, Korteweg and his pupil De Vries proposed equation at the top of these slides. Later, it was shown that this equation possesses a special particular solution of this type, and this solution, as from mathematical point of view, is a quickly decreasing function. The function is disappear more quickly than any derivative of this and any polynomial. So, in the middle of the last century, a lot of the studies were devoted to this equation. First of all, these studies appeared in relation with famous Fermi-Pastor-Ulam problem. And due to the problem, papers on investigation by Kruskal and Zabursky, who rediscover Korteweg-De Vries equation, they give explanation of this phenomena, and from this time of discover oscillatory wave for the second time by Kruskal and Zabursky, now in theoretical manner, this equation, Korteweg-De Vries equation, became very popular for investigation, first of all by physicians and later by mathematicians. At the same time, it was proposed a new mechanism called inverse scattering transform for calculation of particular solution of special kind, and this special kind solution were very, very interesting. Due to Kruskal and Zabursky, such particular solution are named like soliton or soliton waves, and these soliton waves are described namely the formula number 2 from the top to bottom. Later it was discovered that this equation also possesses a different kind of special kind of solution called M-phase soliton solution. What is M-phase soliton solution? It is a nonlinear impulse that in the middle is some nonlinear phenomenon, nonlinear impulse, but when arguments tend to infinity, this impulse consists of some unique soliton impulse. In this case, it is said that soliton, M soliton solution can describe interaction of one soliton solution like this. Because soliton solution has some specific feature, for example, the velocity of soliton solution is proposed to the amplitude of soliton. These soliton interact like particles, so without change of their form. And this soliton solution or soliton waves are localized in space and in time. So the main part of soliton waves is the sum space of space and time. Later, we discussed interesting formula for description of M-soliton solution. You can see this formula in beautiful form at the slide, and you can see also the description of this element of this formula. Since maybe instantly with these studies of soliton property or soliton prover system, where appear a lot of papers devoted to study traditional question on pure mathematics for new equation, in this case. So a lot of paper were devoted to investigation this KdV equation. First of all, I would like to mention some paper by, you can see names of the scientists who studied this equation and different direction or in what this equation was studied. You can see problem of existence, uniqueness, smoothness, existence of solution with specific features, soliton, periodic, and also at the same time, new paper devoted to asymptotic analysis of this kind of equation appeared. In this connection, I would like to mention paper by Kruskal, Miura, Lux, and Livermore, the curve, Flashka, Forrest, McLaughlin, Ablovis, and others. So, I write the title of this lecture without words, the nonlinear VKB techniques, because tomorrow I will tell about these techniques in more details. Now, I want to attract your attention to some problem connected with asymptotic soliton-like solution of KdV equation. So in 1974, you see a reference for this as a correspondent paper. Kruskal and Miura proposed so-called nonlinear VKB technique. VKB technique were proposed at the beginning of the last centuries. Lux and Livermore studied weak limits of solution to KdV equation with small derivative at the high derivative, equation number 2. They published three paper of big volume in Communication Pure and Applied Mathematics in 1983. You see a reference for this paper. And now a few words about the VKB technique. This method was proposed for the description of approximate solution of Schrödinger equation with variable potential. If you consider Schrödinger equation number 3, and according to this method, VKB technique, you will seek for a solution in the form of 4, you receive a nonlinear equation instead of linear equation number 3. Later, we introduce new unknown function because wave function psi is complex valued function. So we used a function for real and imagined part of first derivative of this function, and after substitution of equation in form of 6, we obtained some system of equation where, according to the ideas of asymptotic techniques, we deduce equation number 5. Later, this equation number 5 are studied by using of asymptotic expansion 6 and coefficient and equation for determination of coefficient of expansion number 6 will be deduced. It is the idea of this methods. Tomorrow I will tell you more detail about this approach. Now I want to say about a few words about term nonlinear VKB technique, because presented before the previous slides techniques is related with linear depends of small parameter. Now here constant Planck constant is considered as a small parameter. So in general case, in case of nonlinear VKB technique is used representation number 8. So this representation of formal expansion is more general than initial representation like 6, it seems to me. Okay, at the previous slide. The problem under consideration in this lection is the KdV equation with variable coefficient equation number 9. This equation is a direct generalization of KdV equation. Instead of a constant coefficient near the time derivative and near nonlinear terms, we consider some function which are variable in x and t, and in addition we add small parameter, because such model may be considered as a model that describe move of waves in homogeneous media. In homogeneous media, which characteristic can change in space and in time. We presuppose naturally that the main terms of expansion term are not zero. And also we consider this expansion for expansion number 10 and equations corresponding to equation number 9 for space variable from all real axis, and for some for t from some finite interval. We consider finite interval because in general, due to consideration general case, the interval where a solution may be exist in time variable may be only bounded. It depends of solution of some nonlinear equation for so-called space function, phase function. I would like also to recall some paper devoted to consideration of KdV type equation. Maybe the first paper was published in about 40 years ago by Maslov and Milyanov. It was equation number 11. They consider a particular case of KdV type equation, but it is not the same form of solution of equation because there is additional terms, the last term and term for the derivative in x of the first order. Here h of x is the height of liquid over bottom. In this particular case, and this problem is connected with description of some special model. So I recall you definition of asymptotic series in accordance with Poincaré. You can see this definition at the first lecture, and in sequel we will use the space or quickly decreasing function or Schwarz space. So we denote by S or R the space of quickly decreasing function. This function are infinitely differentiable for all x and for any integer m and n. The following condition holds. Here we have derivatives of function, and so this function tends to 0 more quickly than any power of x when independent variables tends to infinity. Okay. Now we introduce some functional space which we need for construction of soliton solution. As you can see before, the soliton solution is a quickly decreasing function in variable in difference x minus at. X minus at will be phase of this solution. So we consider some space of function which have infinite number of derivatives, and in addition we suppose suppose that there is some subspace of this function space G. G is quickly decreasing function in variable tau, Here in definition, we used denotes F minus, is some maybe basement of a solution because this function is the limit function in the case when derivative with respect to tau has zero order. So the main definition which we need for follow for further is definition of asymptotic one-phase soliton-like solution. Here we use term one-phase because as in general case, KdV equation has two and multi-phase soliton solution. So if we consider the KdV equation with variable coefficient, we suppose that due to variable coefficient, the special solution, soliton solution, will be have some deformation, small deformation, which depends of perturbation of coefficient. So here we have phi of t. So it is a real value function, and this function is called phase function. Difference between x and phi is called a phase function, phase of this solution. In general, when we consider properties of soliton-like solution, you can see that when small parameter tends to infinity, infinite plus or minus, the limiting function will be equal to zero. So only in one case, when this difference x minus phi is equal to zero, the solution will be has some maybe not zero limits. So in this case, we have some curves on the phase plane, and this curve is called discontinuity curve. Now we consider a form of asymptotic solution. In general case, when power of singularity number n, natural n, can be arbitrary, general condition asymptotic solution depends of the number power of singularity, and according to the general basement of asymptotic theory, we consider several problems. First problem, we must define the form of asymptotic solution. It will be do later. And the next problem is justification of this algorithm. And also the next set problem is construction some example which demonstrate the this algorithm which can perform, which can show that this algorithm is fruitful. So the problem under consideration is solved in several steps. Several steps. First of all, we specify and form our asymptotic solutions. Later, we deduce equation for the terms of asymptotic expansion and solve this equation. The step is a definition of phase function phi, and the last steps is connected with asymptotic estimation for constructed asymptotic solution. So here we consider the two different cases. If we have Cauchy problem, we can estimate difference between exact solution and constructed asymptotic solution, the second case. But in the case when we have no Cauchy problem, no Cauchy data, we must estimate how construct solution satisfy the initial equation. So we will consider only the problem without Cauchy problem, without initial data, and later I will demonstrate for you some particular example which prove the fruitfulness of this algorithm. So, in general case, we represent asymptotic solution in form number 5. We have the first sum, it is a regular part of asymptotic. This part of asymptotic do not depend on tau variables, and the second part is a singular part of asymptotics. It is similar, the idea of boundary layer function, when we also have the regular part of asymptotic and the singular part asymptotic, and this singular part asymptotic contains small parameter in denominator. So for different type of natural n of power singularity, we have two form of asymptotic. The first case of the odd power asymptotics, we have very nice representation of asymptotic solution, but in the second part, when n is even, we have more complicated form of asymptotic solution, because this expansion, number 6, contain fraction power of small parameter. So this details this point complicated in just complicated a problem under consideration. In further, we will consider case now when power of singularity equals 2, and in this case, asymptotic solution has form number 7, and regular part of asymptotic is represented by formula number 8, and singular part of asymptotic is represented with formula number 9. Now I return to KdV equation with small parameter near the higher derivatives. Equation number 10. Of course, by the simple change of variables, by rescaling, we can rewrite this equation as classic KdV equation. In this case, when we return to the first variables, we obtain solution represented and in formula by formula in the below bottom of this slide. You can see that small parameter located in the denominator of this arguments of function, and function cosine minus 2 is quickly decreasing function of variable tau, which we consider like tau, I don't know. Okay, there is not marker. Okay, because I don't know. Here you can see graph of Soliton solution for KdV equation for different values of small parameter. For small parameter, it is similar, but you have some difference between these two graphs. I show these graphs because later, at the end of this presentation, this lecture, I will show some example, which is light deformation of this solution, of these graphs. So maybe if you need, I will go back to these graphs, and now we consider the construction of asymptotic solution. First of all, we consider equation for regular part of asymptotic solution. In this case, we use properties of singular part of asymptotic with ends independent variable tau to infinity, and we deduce equation for regular part of asymptotic. As you can see, the first equation is nonlinear equation, and the other equation are linear equation. From mathematical physics or from theory of differential equation, partial differential equation, you know that this equation can be solved in general by method of characteristic. In the first case, for the for the function u sub 0, it is just a little complicated, but for the other high term of asymptotic of regular term, it is more simply. If we, for example, want to consider a particular case of coefficients a and b, for example, when this coefficient can be factorized or can be represented as production of function over x and function of t independent. So in this case, we can easily to obtain exact solution of equation number 11 and equation number 12. It is the first remark. The second remark is the following, that equation 11 can be considered as Hopf equation, which is known as equation of discontinuity in hydrodynamics. This equation is studied very well, and for Hopf equation, as you know, may be so-called gradient catastrophe when the function solution or the first derivative of this equation can tend to infinite. So, in general, problem of determination of regular path of asymptotics may be considered as solved problem, but from the other point, this problem is not very easy, not very simple, because in some particular case, it depends from initial data for equation 11. Solution of this equation may be destroyed on definite part of complex in plane. So it is more complicated problem for solution of for determination of singular terms of asymptotics. In this case, first of all, we have the equation of the set order. Here we consider variable x and t as independent of variable t. It is convenient because we enlarge the dimension of unknown function. In this connection, we also have the following situation. The first equation can be solved exactly, and besides that this equation is nonlinear. And the first equation number set, has a solution like Seleton solution. You can see a formula for this solution. And the other equation, number 14, is linear equation, and it can solve by the method of ordinary differential equation, because coefficients of this equation are independent of variable tau. The right side of this equation are determined recurrently and can be easy calculate if you want, how much if you want. So now some elements of technique for the determination of terms on singular path asymptotics. First of all, I would like to attract your attention to the following feature of this problem. The solution of this problem for singular path asymptotic have to belong to some spaces. These spaces was introduced before at the beginning of this lecture. So we have also additional unknown function. It is phase function, or function that is determined the discontinuity curve. This function is determined during this solution of some specific equation, and it is equation for the determination of this function is a sequence of solvability of particular equation in special terms, in special spaces, G sub 0 and G. Also, this is the first remark. The second remark is the following, that we do seeking of unknown function the following way. First of all, we suppose that phase function is known. Later, we consider unknown function over this curve of discontinuity. And later, we deduce equation for this function v sub v from t and tau over discontinued terms. Later, we analyze this equation. If solution of this equation belongs to the quickly decreasing function in variable tau, we can put prolongation of this equation, this function from discontinued curve with simple way. We put v big, large, like v small. If this condition not fulfilled, we do the prolongation from discontinuous camps in his neighborhood in some special way. We used some special representation of these solutions for the general case. So we consider the equation for the general term, main term on the major term of a singular part of asymptotics, equation number 15. Under simple assumption number 16, we find exact solution of equation number 15 in form number 17. Here appears some constant, and as you can see, this formula is similar to formula for Seleton solution. If coefficient A and B are constant, you have the same solution. So function number 7 are like Seleton function, and it represents some deformation of Seleton solution. The next equation, number 18, is equation for other term, higher term of asymptotics on the discontinuity curve. We reduce problem 18 to the problem of lower order to the second order differential equation, and we obtain some second order differential equation. But equation number 18. But we have this equation, and we want to have this to find solution to this equation in a space of quickly decreasing function. So it is principle maybe a question or problem under what kind of condition for potential of this operator and right side function, solution of equation 18 can belong or can exist in the space of quickly decreasing function. No, as is this proved, it is possible in the case when function q can be represented in the form constant plus constant must be negative and plus some quickly decreasing function. Later, this result is formulated in the terms of kernel of operator L acting from quickly decreasing acting through the space of quickly decreasing function into space of quickly decreasing function. So if kernel operator L is trivial, then equation 19 has solution in this space quickly decreasing function for any right side function f. I show again, I show again equation number 19. It is very simple, but the specific feature of this problem is the following, that we must find solution in space of quickly decreasing function. Otherwise, if kernel operator is not trivial, the equation has a solution only if function f satisfies the orthogonality condition. Here, v sub 0 is a solution for the major or main term of singular part asymptotic, and would like to remark that kernel of operator L can consist only of one independent function, because in the case if this kernel consists of two independent functions, accordance with formula for Wronskian, we use that equation disappear. So now we continue to analyze equation for singular part of asymptotics. We are interested in solution of equation 18 and using of theorem and orthogonality condition, interorthogonality condition, we deduce a condition under which equation number 18 has solution in the space of G. It is suitable for us, but in this case, continuity obtaining solution from discontinuous cam to its neighborhood is more complicated. So we want to obtain a condition under which equation 18 will have solution in space of quickly decreasing function. This result, okay. This result is given by lemma 2. So if right side function belongs to space of quickly decreasing function with respect to variable t, and orthogonality condition, what we saw show at the previous slide, take place, then function of singular term of asymptotics is belong to space of quickly decreasing function if and only if the condition 22 holds. So, and for case when the condition of this lemma do not fulfilled, we have a representation of solution of equation 18 in the form the first row on the top of this slide. So we have here some function phi from space G sub 0. It is a little small mistakes. Function eta belongs to space G, and this function has these properties. And later it is described some elements of formula of this representation. I also called you some simple results from theory of function. For example, if you have some function which is 0, 0 on this path of real number, and real is equal to 1 to unit on the other part, but between interval where this function has different values, there is some construction, there exists function which will be infinitely differentiable, and this function will be equal to 0 on the left part and equal to unit on the right part of this graphics. It is the form of function. Yeah, it is not important, but it is maybe different function. So this representation for formula number 1 is similar to these results. So when we applied orthogonality condition, we deduce equation for phase function, equation number 23. As you can see, it is complicated equation. It is nonlinear equation. In general case, this equation may be very tedious, but in particular case, for example, when remarks 2, when there is some special relation between main terms of asymptotic expansion for coefficient, this equation for phase function is simplified it. And this relation will be used for consideration or construction of particular case or particular example for demonstration of these techniques. So, okay. So I want to recall again, I will tell you again that if singular part of asymptotic belong to quickly decreasing function space, we can put prolongation by very simple formula. In the other case, we use representation which was shown before. Later, for construction of continuation, we consider additional Cauchy problem with first order differential equation. You can see equation number 25 with operator lambda. Also, you can apply also characteristic methods of characteristic. These methods allow you to construct solution with this initial problem, and in particular case of coefficient, you can easily construct exact solution of initial problem number 5. So the general statement about estimation accuracy for constructed asymptotic solution, because as you remember, we pointed that the regular part of asymptotic we can consider is defined, it is known, and now I describe you in general algorithm for construction of singular part of asymptotic. So we collect together this part of asymptotic, it can estimate the accuracy with which this constructed asymptotic solution satisfy the KdV equation under consideration. So under some condition, quite general condition, you see we suppose coefficient of expansion be infinitely differentiable, some additional condition, condition number 2, and the right side function in equation for singular terms in equation 18 belongs to space G1 and condition orthogonality, we deduce that constructed solution, constructed solution number 26, particular case of constructed solution satisfied initial differential equation 23, equation 3 with accuracy O large epsilon n. So the other kind of statement about asymptotic accuracy is connected with existence of solution of problem addition Cauchy problem. In this case, we have another form of asymptotic solution, and we have the same type of accuracy. Now I proceed to maybe from my point of view, the most interesting part of this representation and to consideration particular case examples. So we consider equation number 1. If you can see, it is KdV-like equation with variable coefficient. Of course, this equation cannot be deduced or deduced to the form of KdV equation. We see additional condition for coefficient of expansion. In this case, we have only first term of asymptotic expansion for coefficient. The special condition about which I told you before, simplifying the equation for phase function, it is equation number 2. It is very easy to find exact solution of equation number 2. This solution has form number 3, and this case it is very important that function phi is defined for all value of time variable. So the solution is global because in general case for phase function, as you can see, this equation is nonlinear. This equation has only local solution, not general, not global. In this case, in this example, we have global solution for phase function. So constructed soliton-like solution will be like soliton, solitary wave in common features. So later we deduce equation for the main term of singular part of asymptotic. We suppose that regular part of asymptotic is equal to 0. It is adopted because in this case basement of soliton solution is 0, and we find the exact solution for main term. This solution has soliton-like form, and this function belongs to space of quickly decreasing function with respect to variable tau. So we can consider the main term of asymptotic, and you see the corresponding graphs of constructed asymptotic-like solution for variable coefficient KdV equation. For the same value of small parameter for graph what was shown for you before for exact soliton solution. You can see some deformation of soliton solution which are similar. So, and the next term of asymptotic expansion, the next for calculation, this next term, first terms, we need to calculate some additional function. There is here are presented concrete value of this function, equation for determination of the first term, and corresponding right side function. So it can be solved exactly, and we use formula number 6 for the first term of asymptotic solution. So finally, we obtain the first approximation of soliton-like solution in form number 7, and here equation, the first term, the zero, the main term, and the first term are given by formula presented at the previous slides. So in this case, we also construct some graphs for at the same value of small parameter, and you have some more deformation of this soliton solution, but this soliton solution has global, is global, so it is defined for all x and t, for all space and time variables, for all values of space and time variables. So that's all. Thank you very much.
Credit on whatever the risk equation. Is it important? The technique is bound to this equation particularly, or even it is more general and would be applied to.
Yes, this technique can be applied to other kind of equation. First of all, it was applied to BBM equation, Benjamin-Boni-Mahoney equation. Corresponding paper is published in Journal of Mathematical Physics in 19. Later to Burger's equation. And to Kamasa-Holm equation, Kamasa-Holm equation. This Kamasa-Holm equation is some generalization of KdV equation. And BBM equation, Benjamin-Boni equation, is along it was a product or result attempts to generalize or to find alternative of KdV equation. But if the KdV equation is incurable system, this equation has infinite set of conservation law, and these conservation laws are in involution. But BBM equation has only 2 or 3 conservation law, and BBM equation is not integrable system. But this equation has soliton type solutions. Soliton type. Да, soliton type. Yes. The main form of solution of BBM equation is like soliton solution, but they have remainder for the large value of variables. Remainder remains. Okay. And there is also other example constructed for this solution, for this exact example constructed for this equation with specific values of coefficient. And the results are similar, but in every case we applied non-linear VKB techniques, but in every case we must modify these techniques to for application this technique to special equations under what we consider.